People, this is our discussion of the intermediate value theorem, and this is how it's stated in Ron Larson's calculus book. It's stated that way in a lot of books. Most people run into it for the first time when you're dealing with the solution to polynomial functions, and I'll explain why that is here in just a second. But the intermediate value theorem is one of those theorems that, and I don't know what the official term, the umbrella term is, it's basically an existence theorem, okay? It basically says, if certain things are true, then such and such must exist, okay? So if f is continuous on the closed interval a, b, and of course, all polynomial functions are continuous everywhere, which is why it's relevant for polynomial functions. So if f is continuous on some interval a to b, and f of a is not equal to f of b, then and k is any number between f of a and f of b, then there is at least one number c in AB such that f of c is equal to k. Now, here's what that looks like. Let's say that this over here is A, and this over here is B. Okay, so basically f has to be continuous on this interval. Okay, good enough. Now, f of A is not f of B, so let's call this right here f of A. And let's call this right here f of b, right? Because when you plug in b, you get that output, so it's f of b. And therefore, f of a and f of b are clearly different outputs. They are not equal, okay? So there is any, okay, and k is any number between there. So k can be any number between f of a and f of b. Then there is at least one number c in AB. So basically, there has to be a number between A and B that gives you K. Okay? And that's because if it's continuous from A to B, then in order to draw this function from A f of A, this ordered pair down here, to B f of B, I have to do so without picking up my pencil, right? And therefore, I have to pass through every x value between A and B and every output value, y value, f of x value between f of A and f of B. Okay? So if you're choosing some arbitrary number between f of A and f of B, then there has to be at least one input that corresponds to that output. Now, that's really helpful if your k value that you've chosen is output is equal to 0. And if A f of A and B f of B give you outputs that are opposite sign, the implication is somewhere between A and B there has to be a 0. It has to cross the x-axis because I can't get from f of A to B f of B without crossing. Now, it doesn't tell me whether there's more than one, and it doesn't tell me exactly where on that interval it lies. It just says if f is continuous, then there has to be a 0. Okay, that's sort of the payoff. Now, according to the way that the intermediate value theorem is phrased, it doesn't have to be that, but we use it when we're dealing with polynomial functions. And I'll show you what I mean. Let's go back and let's do a little review of sort of the rational root theorem questions. Now remember, when you're given something like this and you can't see the factorization, you have to do your p over q values, right? So my p values are, plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 8, plus or minus 12, and plus or minus 24. And you get your q values, and that's plus or minus 1 and plus or minus 2. Now you get your p over q values, and it's basically just all of these. It's all the p values because you divide them by 1. And then the q values are the ones that don't repeat when you start dividing them by 2. 8, which of course is only the odd one, which is 3. And then you get plus or minus 3 halves, right? Okay, and at this point, if you don't remember, what you start doing is you start doing a whole lot of synthetic division, okay? And so let's do 2, 7, negative 10, negative 24, and let's say, let's do negative 2, okay? So negative 2, we have 2, and this becomes negative 4, and so that's 3, it's negative 6, negative 16, and 32, and our remainder is a positive 8. Okay, well that doesn't work. Let's try negative 1 and see whether it works. Okay, so we have 2. Begins negative 2, it's 5. That gives you negative 5. That gives you negative 15. And that gives you positive 15 and negative 9. Now, what this means right here is you have the ordered pair negative 2, positive 8 because of the remainder theorem, right? Remember, the remainder is also the output at negative 2. This right here tells me that I have negative 1, negative 9. This is a polynomial function, so basically what happens here is at negative 2, I'm up here at positive 8. At negative 1, I'm down here at negative 9. There has to be a 0 somewhere in here, because in order to get from here to here, and this is a cubic, so we know that the shape does something like that, right? And this is basically coming down. It basically has to happen. I have to cross between negative 2 and negative 1 if there is a change in sign of the output, because it's a polynomial. It's continuous. I can't pick up my pencil, or in this case pen, as I'm drawing from negative 2 to negative 1, and therefore it has to take on every output value between them. And in fact, what happens here is what you find out is the fact that negative 3 halves is your 0. Okay, so that's what the intermediate value theorem says. Now, the last question that we need to ask ourselves is, if the IVT does not apply, and therefore does not guarantee zeros, is it still possible for the function to have zeros on the interval? And the answer is yes, okay? Basically, it's saying, given these certain circumstances, if these certain criteria are met, then such and such must exist, okay? And that's kind of what we're going for. So if we're using IVT, it says use the intermediate value theorem to determine whether the given function must have a 0 on the given interval. And it winds up being relatively easy. We simply have to plug in negative 2, which is negative 2 cubed minus 3 times negative 2, which gives me negative 8 plus 6, or negative 2. And then I need to plug in 2, and I'm going to get 2 cubed minus 3 times 2, which is 8 minus 6, or positive 2. So this gives me the order pair negative 2, negative 2. This gives me the order pair 2, 2. And the answer is, do I necessarily have a 0 on this interval? Do I necessarily have an x-intercept? And the answer is yes, because in order to get from negative 2, negative 2 to positive 2, positive 2, since I can't pick up my pencil as I'm drawing this, I have to go through the x-axis. And therefore, yes, okay, it is confirmed. Now, and that's basically it, okay? You just have to remember the criteria that are laid out. And the criteria that are laid out is, if f is continuous, and anytime we have a polynomial function, it always is, on the closed interval a to b, and f of a is not equal to f of b, meaning the endpoints don't have the same output, and k is any number between there, Okay, so you have to have those three things checked off. It needs to be continuous on the interval, the outputs on the endpoints of the interval can't be the same, and the value that you're looking for has to be somewhere between those outputs, somewhere on that y, that output interval. All right, then that means that there is at least one C value, there is some input value that will give you that output value. That's what it's saying. Now this one right here, if we go ahead, and this is on the same interval, if we go ahead and look at this one, let's go ahead and plug in negative 2 to the fourth minus 1, so that's 16 minus 1, or 15. F of 2 is positive 2 to the fourth. Well, that also gives you 16 minus 1, or 15. And so basically you have negative 2, 15, and 2, 15. Well, those have the same output. In this case, f of a is equal to f of b. So one of the criteria fails, and the intermediate value theorem does not apply. Now, simply because it doesn't apply, does that mean that I don't have zeros? No, and in fact, you have zeros on this interval. You have one at 1 and one at negative 1, which are both inside this interval. And you can get that by factoring. All that's going on here is the fact that you are not guaranteed those zeros using the intermediate value theorem. That's all it's saying. So it's not saying that they don't exist. So it doesn't disprove the existence of those particular values. It just can't confirm them based upon the criteria and the logic that sort of governs it. All right, let's go ahead and look at one more in terms of a function, and then we'll look at an equation one. Okay, so f of x is equal to the square root of x squared plus 4x minus 2 in 0, 1. Okay, well, it's worded a little bit differently, but you're still dealing with an interval, and you're still looking at the endpoints of that interval. So what you have here is the square root of 0 squared plus 4 times 0 minus 2, or negative 2. That gives me the ordered pair 0, negative 2. Let's go ahead and plug in 1, and you're going to get 1 squared plus 4 times 1 minus 2, and that's going to be the square root of 5 minus 2, which is approximately 0.828, okay? And so that's going to give you 1 positive 0.828. And the question is, does that necessitate a 0 on this interval between 0 and 1? And the answer is yes, because at 0, I have this, and at 1, I have this. Well, is that necessarily the case? Well, we haven't checked for continuity yet, and I guess the question is there anything that prohibits taking on the values between 0 and 1? And the answer is no, okay? Because if you basically put this into factored form underneath the radical, the only things that are disallowed, that don't make sense, that would cause a problem, are values that make the radicand negative. And the radicand can't be negative, but for values in 0 to 1, the radicand is going to be positive, and therefore there's no issue, okay? And there's not going to be any jumps, there's not going to be any asymptotes, there's not going to be any holes, there's no domain breaks on that interval. All we have is between 0 and negative 2 and 1. And I can go ahead, let's go ahead and graph this function. I think that this is a good one to actually stop and, okay. Let's do the square root of x times, and I'm going to put it in factored form just because I don't feel like doing the squared notation. Now, if we look at the window, let's go from 0, let's go from negative 1 to 3. Actually, let's go from negative 2 to 3. And then let's go on a scale of 1. And then let's go from negative 3 to 2. Okay. Now, 2, 8. Oh, no. That's wrong. It's root 5 is 2.323, I think, or something like that. So I got the wrong thing, but it's still positive, and that's what we're really about anyway. That's what we're really looking for, is a change in sign. You know, that definitely is not 0.8. But what we do see there is we do see the necessity of the 0 because, and let's go ahead and change the window to our actual window, right? Our actual interval. And what we have here is we see at 0, -2, and we see it necessarily crossing because right up here we have a positive value, and we see it's continuous, right? There's no breaks, there's no jumps, there's no asymptotes, and therefore a 0 somewhere on this interval was guaranteed. Yes. All right. Now, can we use that for something like this, a messy equation like this? And the answer is yes, because where these two will be equal, this will be 0. So really what you're looking for is you're basically what you want to do is you want to take that equation and you want to transform it into a question about a function like above, like all the 3 that we've done prior to this. And the question is, okay, well, is this continuous on 0 to 1? Okay, well, first of all, we can just do it term by term, or just at least look at it as an exponential plus a linear. Exponential functions are continuous everywhere and actually have a domain of -infinity to infinity. Polynomials, same thing, right? Because linears are just the simplest polynomial functions. And so why would the sum of an exponential and a polynomial, both having those characteristics, not have those characteristics as well? And they would, okay? So all you have to do from here is evaluate f of 0. Well, that's e of 0 plus 2 times 0 minus 3. So that's 1 plus 0 minus 3, or -2. That gives us the ordered pair 0, -2. Okay, well, let's evaluate it at 1, and that's e to the first plus 2 times 1 minus 3, and that winds up being e minus 1. Well, e is 2.718, so this is approximately 1.718, and I'm going to get 1.718, and I do, okay? I know that the function is continuous on the interval. The outputs are not the same, and therefore I should be able to find a 0 between these two. And let's go ahead and take a look. Okay, let's go ahead and just plop that in there. And we know that e to the x plus 2x minus 3, and we already have the interval because it's the same 0 to 1 as up here. We already have the window where it should be. So let's just go ahead and graph. And we see that we see the 0 that we were guaranteed. Okay. Now you got to remember that it will, like, could there have been 3 zeros between there? Sure. There could have been more than one, but you're guaranteed at least one because the outputs have changed sign. And if the outputs have changed sign, the outputs must go through all of the values between one and the other, and those values, of course, include the 0, and therefore it must cross the axis. And we can see how why intermediate value theorem is brought up again here during the discussion of continuity, because it is a theorem that is based upon the issue of continuity and shows continuity's significance. Okay, that's just about all we have. I think that's enough for IVT, and we can sort of clean that up a little bit in class if necessary. As always, if you have any questions, do shoot me an email. Bye.